When you fill the electrons, there are certain rules that you have to follow. One of them we already talked about. For each room, for each orbital, you can only have 2 electrons in there. Now, the electrons will also fill according to the energy level. It goes to the lowest energy level first, 1n. N equals 1, 1s. That's the lowest energy level. That's the hotel room on the ground floor. Okay. So when you have 1 electron, you put it in there. When you have 2 electrons, you put them in there. When you have the third electron will have to go to 2s. The fourth electron also goes to 2s. And then if you have the fifth electron coming in, the fifth electron will go to 2p. So this is the sequence there. And follow the arrows there, and you will be able to determine the sequence. Where does the electron go? Now, when we're talking about the periodic laws and periodic rules in the governing the periodic property, we are, in general, we're talking about, in general, this is what's going to happen. There's always going to be exceptions. And this is very much like what happens in our society. And there are rules and there are regulations. There's always exceptions to them. And some people may sometimes may feel that they are above the law and they can be exempt from the rules there. So there are always going to be those exemptions there. But this is in general. This is how we fill up the orbitals, and we call it electron assignment. So electrons occupy the lowest energy orbital available, beginning with 1s and going up to 2s and 2p, 3s and 3p. And you may think after 3p, you go to 3d. But hey, that may not be the case. And again, each orbital can hold only 2 electrons. And if you do have 2 electrons in there, they must spin to the opposite direction. That's the Pauli exclusion principle. Okay. And the set of orbitals with the same energy are each half filled by 1 electron before pairing starts. So when you go to the 2p orbital, 2p sublevel, you have 3 orbitals in there, px, py, and pz. So you got 3 rooms on that sublevel. You are the hotel manager. 1 electron comes in, okay, you put them in one of the rooms. The second electron comes in, you don't pair them up in the room. You have 2 other vacant rooms there. So give the second electron a private room. Third electron comes in, give the third electron a private room. Okay. Each room is half occupied. If you have the fourth electron coming in, then you start pairing them up. Okay, so that's what this particular rule is all about. And you can only have a double occupancy there, so you only put 2 electrons in each room, but you don't pair them up when you have enough rooms to give each electron a private room. So this is the rule that we're talking about there. Now this particular sequence is not something that I need you to memorize. If I asked you the electron configuration, the filling of the electrons there, the sequence of filling of the electron filling there, I will give you this diagram. You will be able to look at this and simply follow the arrow and try to determine the sequence where the electrons are being assigned in a particular atom, in the atoms of particular elements there. Okay, so here orbital filling, and we have different rules governing the orbital filling. The alpha principle, basically the first thing that we said on the previous slide there, lowest energy orbital will fill first. Okay, when the orbital with the lower energy is filled, each one with 2 electrons, and then electron will have to go to a higher energy level. Now this is just like everything that happens in nature here. Okay, if you can do less, you don't want to do more. If you don't want to spend, if you can spend less amount of energy to do one thing, you don't want to spend more energy to do something. So electron will fill to the lowest energy level first. And when the lowest energy level is occupied and filled, you go up to the next level, to the higher level. Now Hahm's rule says degenerate orbitals, that's the px, py, pz, or the 5d orbitals. They're degenerate orbitals, meaning those with the same energy. So if you have s sublevel versus p sublevel on the second and on n equals to 2, the p sublevel is considered as a slightly higher energy than the s sublevel. But the 3p orbitals are considered as degenerate orbitals. Px, py, and pz, they have the same amount of energy. Okay, so if you have a set of orbitals that have the same amount of energy, then each of the orbitals is filled with one electron first, before pairing starts. Okay. So again, it's a sense like when you have 3 rooms on the sublevel, on a particular level there, and when the guests come in, you want to treat them nice. You want to give each one a private room first, whenever possible. And then if you run out of room on that sublevel, you can start doing double occupancy there. Okay, that's the hung through there. And then Pauli exclusion principle, individual orbitals can only hold up to 2 electrons. If they do have 2 electrons, they must spin on the opposite direction. So this is what governs the filling of the electron around the positively charged center in an atom there. So the s orbital holds up to 2 electrons, p up to 2, p up to 10. Okay, and then the S, P, D, and F up to 14, because F, you have 7 orbitals in there, 7 times 2, 14 electrons. Okay, so 2n squared is the total number of electrons on each n value. Okay, so when you start filling the orbitals there, and you remember that when we're talking about the En equals to negative RHC over n squared, when we give you that diagram there, n equals to 1 versus n equals to 2, actually there is a fairly big difference. But as you go up, the energy level starts to cross over a little bit. So when you go to n equals to 3, you will realize that the energy level of 3D is actually higher than 4s. Honestly, how does that come about? Well, look at this particular diagram. The total energy for a specific sublevel is determined not only by the n value, but also by it's actually determined by the m plus l value. You cannot just consider the n value, you have to take into consideration of the l value. Okay? So m plus l for n equals 1, well, n equals 1, l equals 0. So m plus 1 equals to 1 here. When n equals to 2, for the 2s orbital, and 2s orbital, l equals to 0. So 2 plus 0, n plus l equals to 2. Right? And then for the 2p orbital, n plus l equals to 3, because n equals to 2, l equals to 1 for p orbital. So 2 plus 1 equals to 3. Okay. And then 3s orbital, n plus l also equal to 3, because n equals to 3, and s, l equal to 0, 3 plus 0 is 3. But why does the electron go to 2p first before you go to 3s? Well, because 2 is less than 3. So 2p orbital has a lower energy requirement compared to 3s orbital. And then after 3s, you go to 3p. Now, 3p orbital, n plus l equal to 4. 4s orbital, n plus l also equal to 4. 3d orbital, n equals to 3. D orbital l equal to 2. 3 plus 2 equals to 5. So by the time that you go to 3p, according to the sequence theorem and so on, these are on the same level. Electrons are supposed to go to 3d first. Well, no, it's going to go to 4s. So the total energy of a particular orbital is determined by the value of n plus l. The higher